Wheeler Rummel from the University of New Hampshire, and I'm delighted to welcome you to the session on robot path planning. We have three fantastic talks. The first one is on incremental ARA star, and we'll let Sven Koning describe the work. It's by Yao Jung-sung, William Yo, Tansel Urs, and Sven.
Okay, thank you. So it turns out that actually the first three authors, students or ex-students of mine, really wrote the papers, but no one could make it to the conference, so they sent me instead. So I'll talk about incremental IIIa star, which we believe to be the first anytime incremental search algorithm for moving target search. So our motivation here is actually not robots, it's games. And in particular in games, often you have sort of some game character like this one that I'll call the hunter, and it has to catch up with some other game character like that one here, which I will call the target. Now the target is moving. It could be a friendly character, you just want to catch up with the target to have a chat with them. It could also be a prey, that you want to hunt. Now we are concerned here with the strategy for the hunter. And I make the assumptions here that the hunter knows the trend, the hunter knows his own cell, and the hunter knows the cell of the target. So that's sort of a version of what's called in AI moving target search. Now the hunter could use offline search here. And that's often sort of a form of minimax search, like for example Nathan Sturtevant's reverse minimax E star algorithm. Now offline search has a sort of a disadvantage, and that is that you need to find a huge conditional plan, sort of a policy for the hunter, right? So that for every movements that the target is going to make, the hunter has sort of some response ready. Now that typically is computationally very intensive, which might not be so important if it's offline. But you also need to store the policy, so you need a lot of memory that's usually unwieldy. And therefore, in most cases, what you want to do is an online search. So you want to interleave for the hunter movements with planning. And in this particular case, the hunter can get away with repeated deterministic searches, right? So for example, using the following very, very simple strategy here, the hunter finds a short path from its current cell to the current cell of the target, and then moves along that path. And it keeps doing that as long as the target remains on the path. And when the target leaves the path, then the hunter doesn't quite know how to move. So what it does is it just repeats the process and again finds a short path from its now current position to the current position of the target and moves along that path and so on. So this is a good strategy if the hunter has some kind of a speed advantage over the target. Either can move faster, or the target from time to time makes sort of suboptimal moves so that the hunter can eventually catch the target. So for games, that's actually quite a good strategy, and that's the one that we'll use in this particular talk here. Okay, so how does the hunter implement this strategy? Well, in the simplest case, it just performs an A-star search to find the short path using consistent H values. And this here is how I will illustrate this. So the hunter here will always be on top. The target will always be on the bottom. The blue part here is the expanded states that form the search tree. And then the yellow line here is the path that the hunter finds. And in this case, I mean, since the hunter performs an E-star search with consistent H values, this will be a shortest path. So the hunter moves along this path, and the target moves anyway it wants. It can teleport, whatever. We don't really care what the strategy is. In this case, it moves off the path, and so the hunter performs another E-star search. Now I need to press all of this onto one slide. Okay, so first search here on the left, second search on the right, and then of course there are many more searches that are down here, and I will not show them. Now from time to time I want to show sort of more realistic game scenarios, so using the HOC2 environment here of Nathan Sturtevant. In this case, the hunter will always be to the left, the target somewhere here will always be to the right. The red cells are the cells that were expanded by the E-star search, so on the closed list afterwards. The green cells are the ones that were generated by the E-star search but not expanded, so on the open list afterwards. And again, the yellow cells form the path of the hunter. And during the talk here, I'll always assume that diagonal movements have cost 1, makes it easier for you to count if you're interested in doing this. Okay, so far so good. I mean, this is a decent strategy. Everything that I told you works. There's one small problem. And the small problem is that in games, a lot of the CPU cycles that you have available are used for things like the graphics, right? And whatever little is left for the EI needs to get split often among many, many different agents. So what that means is that you usually have very, very stringent time limits available for the search. And in fact, sort of a couple of years ago, and I think it's the only figure that we have sort of officially in the literature, Vadim Bulitko mentioned that BioWare imposes sort of time limits of 1 to 3 milliseconds for the search. So it gives you sort of some idea of where these time limits are. Now, furthermore, right, so the idea here is that you partition time into sort of equally long time intervals, and then you want the hunter to execute one move in each one of the time intervals. And the reason for this is simply that this way the hunter will move very smoothly, right? And that's important in games as well. So back to our E-star searches. So one of the problems that can arise now is that if you do an E-star search in a larger environment, then the E-star search might not complete within the given time limit. It's not a problem for small terrains. And in larger terrains, I mean, you could use tricks like abstractions and so on, right? But if you want to do a plain E-star search in larger environments, typically we will exceed these time limits. And so the question then is, well, so how do we deal with this? And what we do in the context of this talk here is we want to speed up these E-star searches. Now let me discuss two ideas for speeding up the E-star searches, and they will both become important. So the first one here is simply to use incremental E-star search. So incremental E-star search speeds up the current search by using the experience that you gain with the immediately preceding similar search. So if you have a series of very similar searches, you can use incremental search to speed up the searches. And I want to use sort of a very, very simple, the simplest incremental search that I can think of, and they all have fancy names, so don't let that blind you, okay? This one is called FR E-star. But here's what we are doing, okay? This is again our first search, right? And then the hunter moved and the target moved. But so when we completed the first search, the reason why the search tree is important is because for every cell in the search tree, we have the property that we know a shortest path from the root of the search tree, so the current position of the hunter, to that particular cell, right? And so if the target moves at this particular point, and it moves to somewhere within the search tree, we don't need to do a search, right? We can just read off the shortest path. And that's important, okay? We can capitalize on this. But in this particular case, right, so the hunter moved, the target moved, the hunter now is no longer at the root of the search tree, and so now we need to identify this part of the search tree for which it's still true that we have this property that from the now current position of the hunter to these cells, we already know a shortest path, right? And that's very simple. It's simply the subtree of the search tree that's rooted in the now current position of the hunter. So this particular path, okay? So that part, okay, we keep in memory, we delete sort of the rest. We run around sort of this area, collect the open list, and then we start an E-star search at this particular part. Okay, and it'll run, and the way I'll show this is like this, where sort of this gray area here shows the reuse part. Okay, so the E-star search does not need to do these node expansions because these cells were already in the search tree, and we're just reusing them. And then the dark blue part, as before, shows sort of the amount of effort that the E-star search needs to do in order to complete the search tree. Yes?
So here the red dot is the very same as in the previous situation?
Yep. Okay, and so what this means sort of in our more complicated game environment where I guess the hunter moved from here to here and the target moved to here, right? Is we keep this particular part of the search tree rooted in the now current cell of the hunter. We complete the open list, right, and then we run the E-star search. Okay, so that means this is the first search, right? We didn't speed this up, but then we sped up the second search and all of these subsequent searches using this technique. Now, I don't want to completely mislead you. You can't just look at this area here, right? Because, to complete the open list and so on, you need actually a significant amount of sort of extra operations that I can't quite show here. But it turns out that in our case, actually, you can win quite substantially by doing that instead of doing a complete E-star search. However, there's one thing that I'm always very worried about, and that's why there's always sort of a big disclaimer here if you look into the paper. And it basically says we don't have a good theory for incremental search to some degree, right? Because we are talking about small time intervals, the big O analysis doesn't apply, and so it really all depends on the circumstances, right? On how you implement the algorithms. For example, which data structure you use to implement the priority queue of the algorithm, right? We always use a binary heap. It's pretty slow data structure, but also a pretty general one, which is why you use it, also pretty simple to implement. But if you use faster data structures, for example, it's not necessarily the case that this trick here will win, right? It can also change if it wins, or how much it wins, okay? But in our case here this works actually quite well. So that's idea number one. Let's go to a completely different idea. So here's idea number two. Now we reduce the runtime of the A-star search with a weighted A-star search. Well, so you all know, right? So if we calculate F values like this, if the weight is 1, we get an A-star search. As we increase the weight, typically the search time goes down, but also the path length of the path that we find goes up. Okay, and I'm just demonstrating this quickly here for you. Where the hunter, I guess, is here. The target is here. If we search this with weight 2.5, the A-star search takes 13 cell expansions. Search it with a weight of 1.5, 15 expansions. With a weight of 1, that's the A-star search, 20 expansions. So the runtime indeed goes up. The path length goes down. Here it's 11. It's still 11 in the small environment. Here it's 10, and that's the shortest path. And of course, that's even more pronounced if we go to these more realistic environments. So compare the red area sort of as a proxy for the runtime against the length of the yellow path. Here's a weight of 1.6, 1.4, 1.2, and 1. So here you see this effect sort of very pronounced. And so the idea here then simply is that what we'll do is we'll replace our A-star searches with weighted A-star searches. So that's sort of randomly pick the weight here, weight 2. Okay, so we no longer find the shortest path, and that's what these snake lines here show. So far, so good. Now we have the problem that the time limit is just a soft time limit, but overall, right? I mean, we want to find a path within the time limit, and so typically we want to set the weight very conservatively so that the search completes within the time limit, and so you'll pick a pretty high weight. And so there's a chance that the search completes and you still have time left over, and of course you don't want to waste this time. It's very hard, to given a search problem a time limit to pick a weight so that you need almost all of the time. So now if we have time left over, right, I mean, so we can play the standard trick and say, okay, so in this case, we just run sort of a second weighted A-star search, we decrease the weight a little bit, and if that completes within the time limit, we presumably find sort of a better path that we can use for the hunter, and if there's more time left, right, we can do it again. And so let's assume that at this point in time, the time interval is up, so we can complete the third search, and so this means, right, I mean, that we'll use that path here for the hunter. Now, one of the interesting things here to notice, and if you know this IIIa star algorithm, you know this already, is that if you look at all of the searches that we perform within the given time limit, so this one, and so this partial one here, well, these are very similar searches. Same start, same goal, same terrain. I mean, the only thing that really changes is the weight. And because of this, we can use incremental search to speed up the searches. And there is a technique out there that does this. It's called IIIa star. As I said, all the fancy names by Maxim Likachev. And I'll not tell you how it works. Okay, if you have taken Wheeler's tutorial, you've already talked about this. But I want to show you that it really does work. And so I want to go back to this example that I showed to you earlier. So if we did weighted A-star searches, we need 13, 15, and 20 expansions. And if we use IIIa star, we find the same paths, right? We just find them faster. We find them with 13 expansions, 1 expansion, and 9 expansions. And that is really interesting because if we look at the total number of expansions, these take a little bit longer than weighted A-star expansions. So again, I'm fudging here. But the total number of expansions here is what, 23? Whereas the number of expansions of an A-star search is 20. So with a very small overhead, we get this anytime behavior that we find a path quickly, and then if time is left, we find better and better paths. So that's the second idea, okay? So that's called IIIa star. Now, what I want you to pay attention to is going from this tree here, tree A, this tree here, tree B. And I'll show that to you in a game environment again. So here's tree A, and here's tree B. And not very surprisingly, they very often have a lot of overlap, right? In this case, even more so than during idea 1, because this here is a pretty wide tree, this is a pretty narrow tree. And so it does make sense now to utilize this idea 1 that we had earlier, this FRA star idea, to say, look, we also want reuse, between these two trees. And therefore, we combine these two ideas and give it another fancy name. So we reuse this tree here using idea number 1. Okay, so how much did we actually gain? And my laptop doesn't really react. Okay, so here we go. Now, what we want is we want to be able to perform these searches under very, very stringent time limits. And as I said, in almost all cases, we want the first search to complete. We need that, because otherwise the hunter doesn't have a path. And so I'm going to look at the first searches here, this one and this one. And again, I'll use sort of the dark blue area as a proxy for the runtime. So that gives me this. So this is basically sort of the time that it takes, given the combination. This was the time that it takes using the first idea alone. So you can see that we save significantly for the first search and all of the subsequent searches. And here's the second idea alone, and here we save quite a bit during not the first search, but all of the subsequent searches. So that's basically the win. Okay, so this is the motivation for the paper. Let me quickly tell you on 2 slides what's actually in the paper. So we developed this algorithm, we give pseudocode, and here's sort of the algorithm in English. And it turns out, right, the idea is really, really very simple, but the devil is in the details, right? I mean, here A star needs a longer correctness proof, and here we don't do A star searches, but weighted A star searches. So you need to be very careful how you combine these ideas and exactly what the termination conditions should be, and so on. And so all of this is in the paper. It shows the pseudocode, it explains the pseudocode, it shows the correctness proof, and so on. I'll not bother with this here in the talk. Instead, I'll go sort of directly to the main experimental results, and again, I'll just concentrate on one of the experimental results in the paper. So we use 100 test cases with randomly selected unlocked cells for the hunter and the target. There is a path of the hunter to the target, so the hunter is able to catch the target. And then we do experiments both on 4 neighbor random maps as well as on 4 neighbor game maps. The random maps have 25% randomly blocked cells. The game maps are a version of Warcraft 3. We take all of these domains from the standard repository. That's again Nathan Sturtevant's repository at movingai.com. We use a very simple movement strategy for the target, where the target repeatedly follows the shortest path from its current cell to some randomly selected unblocked cell, and then it skips every 10th move. So the hunter really does have a speed advantage. And when the target reaches its target cell, then it just repeats the process. All of the algorithms were implemented in similar ways. In particular, we did use binary heaps, as I mentioned before, to implement the algorithms. And the time limits here are really soft time limits, in the sense that if one search takes longer, then we let the first search in each time interval complete to avoid having to move the hunter in some greedy way. And then we use sort of a straightforward weight decreasing schedule. The first one that we actually tried out, so it's not really tuned to this particular problem. So we have experiments on random maps as well as on game maps with similar results. So let's quickly look at the game maps. I just want to concentrate on this one here. So pretty stringent time limit, but then again the maps are pretty small. And here's what we see. This is idea 1, idea 2, the combination of the ideas. How long does it take for the hunter to catch the target? So idea number 1 that finds the shortest path always from the hunter to the target is best. That's not really surprising. Here we find suboptimal paths from the hunter to the target, and that results in the hunter taking longer to catch the target. And it really is the case, what I should have said earlier, here we use incremental search to speed up the searches here. And that means that we can perform more searches per time interval than we can do here, and therefore we find better paths for the hunter than we find here, and that means that the hunter reaches the target eventually faster than it does here. And in terms of how well we utilize the time intervals, I'm showing here the percentage of times that the first searches exceed the time limit, right? That's why it's a soft time limit. And so we can see here that these ones here, quite a few searches exceeded, whereas this one here, we sort of hit it quite closely. Okay, so that brings me to the conclusions. Thank you. So in general, right, I mean, replanning is important when the search problem changes. And in particular, right, I mean, in robotics, people often study this case here. So what changes is the knowledge of the hunter. But they study goal-directed navigation in unknown terrain towards a stationary target. And what changes here is the knowledge of the hunter about the terrain, because it learns new things about the terrain as it moves about. We study sort of a different problem, a different reason for replanning, because we study here goal-directed navigation in known terrain towards a moving target. And so what changes here is the knowledge of the hunter about where the target is. So we developed this new algorithm, which is really a combination of two existing ideas, but the devil is really in sort of how to make this technically work. And the idea here is that this algorithm here can be run under very, very stringent time limits and find a path for the hunter. Not necessarily the best one, but a pretty good one. Thank you. Thank you. Okay, any questions?
So is it actually a progression search? Because often in these cases you search backwards from the target to the agent.
Right. Yeah, so in this particular case we do search forward. And moving forward here has an advantage, it turns out, right? And the advantage here is how the start of the search actually moves. Since the hunter follows the path, okay, the root of the tree remains on the path. The target can move any way it likes. If the target remains on the path, great, okay, we can use exactly this trick here. If the target moves away from this, then this really doesn't work, right? And therefore, it's actually important that we search from the hunter towards the target for this particular idea to do well.
Just a little niggly thing. You spoke about this soft time limit, and I noticed that you were exceeding the time limit in a few cases. That quote from BioWare seemed so stringent, like, you know, they will chop off our heads and tell us to leave the room if we take longer than 3 milliseconds or something.
Yeah, so this is a little bit tricky, right? Because it really depends on sort of the obstacles that you see in the environment, how long a search takes. And if you really, really want to stay within this time limit, then usually you cannot guarantee this with full searches. If you do a full search, you want to find a complete path from the hunter to the target, there will be cases, right, where you place the obstacle so that the search actually has to do a lot of effort. And then obviously even weighted A-star searches. We could have set the weight much, much higher, you know, and then go from there. But there is sort of a tricky trade-off, right? If you set the weight too high, right, and then you decrease it, you do a lot of work, right, on very suboptimal paths. And so my feeling here is that you actually gain from viewing this as a soft time limit. You don't have hard time limits. We have some other algorithms that search, say, with a limited look ahead, or algorithms like IIIa, right, that do only a certain number of node expansions, and then guarantee that you find some way of moving the hunter. If you find complete paths, though, you get sort of a much more sensible strategy for the hunter, because the hunter doesn't make any moves that are sort of greedy in the way that immediately afterwards it has to make a move sort of back to where it came from, which looks somehow odd. So my feeling is, I'm not quite sure. I haven't really talked to someone from a game company of whether they could tolerate this or not. They are often very, very worried about sluggish behavior or some behavior that looks unrealistic, right? Because they feel that that's sort of a turn-off for the players. But my feeling is that if they are willing to tolerate this, then viewing this as a soft time bound has huge advantages. It doesn't really sacrifice a whole lot.
Any other questions for Sven? Thank you again. Okay, so this brings us to our second talk, sampling-based coverage. Path planning for inspection of complex structures. What a beautiful picture that is. The work is by Brendan Englund and Franz Hover, and Brendan will be giving the talk today.
Thank you. So yes, I'm Brendan Englund. I'm a PhD student in the MIT Mechanical Engineering Department. And over the course of the next 20 minutes, I'll tell you the story of how we get this picture, which is a feasible full coverage inspection path that not only avoids obstacles, but plans in the presence of hundreds of thousands of coverage constraints. So, the outline of my talk. I'll introduce the problem and some relevant background, and specifically the application in mind here is autonomous in-water ship hull inspection. And then I hope to convince you why the sampling-based planning is important and useful in our specific application where we want to achieve coverage of complex 3D structures. Then I'm going to present a snapshot of the analysis that's in our paper of sampling-based feasible coverage path planning, which we, as others before us, have solved in 2 phases where we break it apart into a group planning problem and a multi-goal path planning problem. And I'll give you a detailed look at the probabilistic completeness of the sampling-based view planning component. Then I'll show you some results from an improvement algorithm we've developed for shortening feasible inspection routes, and some of the theoretical guarantees and computational results that we produced. And then a snapshot of something that we've gotten very recently from a field experiment, actually implementing this algorithm. So, this is the robot that motivates this work, the hovering autonomous underwater vehicle. It's a free-floating, fully actuated, 6 degrees of freedom, hover-capable underwater vehicle. It's quite different from your traditional torpedo-shaped AUV. This is designed to do precision hovering in the vicinity of a structure for inspections. The goal, of course, is an autonomous in-water ship hull inspection with mine detection as the objective. The Navy currently uses teams of divers to sweep ship hulls to look for mines, and they would very much like to automate this task. This project began as a joint effort between MIT Sea Grant and Bluefin Robotics starting in 2002. I've been involved with the project since 2007. And now this has kind of spun out of the lab and is produced as a commercial product by Bluefin Robotics. And 15 have been purchased by the U.S. Navy, and they're currently training on these to perform the inspection. But right now they're using it primarily for this part, which we call the non-complex area of the ship hull, which comprises about 80% of the ship. It's the flat, not very complex components of the hull that you can sweep over using a rectangular back and forth sweep pattern, and using the sonar. In fact, I should say a little bit more about the sonar. The sensor that we're using for this, unfortunately, since we need this vehicle to operate in turbid water environments, we don't have cameras or lasers at our disposal. We have to rely on an imaging and ranging sonar. It's capable of sensing in 2 different modes that I'll describe in a short while. And for navigation relative to the ship hull or relative to the seafloor, we use a Doppler velocity log, which projects 4 acoustic beams either down at the floor or at a wall or at the ship itself, and it gives you your position relative to the hull, which drifts over time, but still is fairly accurate over short time scales. And so we navigate relative to the hull itself to look at the relatively flat portions of the hull. The sonar is operated in what we call imaging mode, in which there's a rather wide vertical aperture, and it's used to produce a flattened 2D image that's several square meters in area, and it gives us a pretty good idea of what's present on the hull. You can't really recover the 3D structure from this type of imagery, though, and so if you have something like a shaft, which you see here, there isn't really much hope of recovering a 3D model from that. But if you're looking at something that's relatively flat, perhaps you could perform a reliable mine detection. And here you can see these zinc anodes on the ship hull stand out pretty well. The problem that I care about specifically is inspecting what we call the complex areas, the remaining 20% of the ship, where you have complex 3D protruding structures. And really, you can't point the DVL at the ship itself. There's too much variation in the structures protruding from different locations that you would lose the DVL lock and your frame of reference for navigating. So we point the DVL at the seafloor instead. And we have to maneuver in the vicinity of these structures and obtain 100% coverage. We're using a slightly different sensor, though. We're using the DITS in basically a range scanning mode, where the vertical aperture gets focused down and you obtain the equivalent of what is a pretty narrow aperture range scan. Although it's fairly noisy, and you're constantly having to deal with the second returns phenomenon of acoustic sensing, where you get competing signals with the objects you're looking at. But nonetheless, it gives us views of these structures. You can see here, this is a scan of a 7 meter diameter propeller and a 1.5 meter diameter shaft. And here's another example in video form of the data as it's coming in, passing underneath the ship, looking up at its shaft and then at its propeller, the same structures that you saw in the previous slide. And another trade-off with this sensor that's pretty interesting for mine detection is we get improved resolution if we're willing to sacrifice the range of the sonar. So if we cut off, in this case, if we have the viewing range, we have twice the resolution in the imagery. And in this case, it allows some of the fouling on this propeller to become a little more easily visible. But this is certainly desirable for mine detection. So we're not only are we taking this expansive structure and trying to cover it with a small robot, but we're also shrinking down the footprint of the sensor and really trying to paint the structure with a pretty small field of view. So there are some assumptions we're making on the robot for this planning problem. We're assuming that the HAUV holds station at each individual location where a view is planned. It sweeps its sensor through 180 degrees of pitch and it collects a volumetric sample, giving it range data of structures on the ship hull. We assume the HAUV has 4 degrees of freedom, X, Y, Z, and yaw. It's not capable of very aggressive maneuvering and roller pitch, and so we simplify it in the following way. We also assume every scan, as we showed in the prior slide, has a 30-degree aperture, and we're looking pretty close to get good views if there are mines in the imagery, so we're looking at about 1 to 3 meters range. So here's the problem statement. The input is a mesh model of the structure that we want to inspect. We have a model of the robot, and we have the geometry of the robot's field of view. The output is a collision-free inspection tour, where the robot begins where it began or ends where it began for easy deployment and recovery. And in that tour observes every vertex in the mesh model. And in the previous mesh models you saw there were hundreds of thousands of vertices. The mesh model is discretized such that if you were to observe every vertex, you would see a mine if the mine was present on the ship hull. You could also orient this problem so that the triangles of the mesh could be observed. That would be a pretty easy reconfiguration to make. The key assumptions are that we have a model-based path planning problem that is geometric in nature. This isn't a very fast-moving vehicle. It tops out at about a quarter meter a second. So really it's a geometric positioning problem where we want to obtain feasible views of the most occluded and low clearance areas at the stern of a ship. And of course, one of the reasons why it's geometric is because the HAUV is heavily dominated by hydrodynamic drag. And as I mentioned before, this is a discrete problem. The robot stabilizes at each configuration and sweeps its sensor before moving to the next configuration. When I refer to discrete and continuous, I refer to the fact that there are often many algorithms in coverage that assume a continuous sensing process where the robot is moving and operating its sensor in continuous time, continuously sampling data as it's moving about its workspace. Here's an example of the desired output. A tour in which the robot stops at each individual waypoint, takes a snapshot with its sensor, moves to the next waypoint. And over the course of this, as you see, each individual sensor snapshot is changing over the course of a color spectrum that we wrap around this tour. The robot's gradually obtaining full coverage of the ship hull by visiting each of these waypoints that were planned. And it should wrap around the end of the rudder and complete its inspection. So the contributions of our work. We believe this is the first probabilistic completeness analysis applied to robot coverage path planning. We take some tools from collision-free path planning and accommodate them, or we modify them to accommodate the vast number of coverage constraints that this problem is facing. We bound the convergence of the sampling-based routines using decaying exponential functions. We also show an improvement algorithm that's it iteratively shortens the coverage routes, and it's also compatible with RRT star, which I'll get to toward the end of the talk, and retains its optimality properties with respect to a local subproblem that we define over this tour. And we'll show some computational and experimental results, as I mentioned earlier. So some prior work in coverage. 2D structures have comprised the vast majority of prior work in coverage path planning. Many of them just look at the problem of covering the open floor area of a 2D workspace and avoiding obstacles. Others look at boundary coverage. These might be a little more ripe for extension to 3D because you can apply them iteratively as 2.5D algorithms and kind of slice through a 3D workspace using them over and over again. Discrete coverage planning in which you stop it, take an individual snapshot with the sensor, has often been captured using the art gallery problem, in which this is kind of a classical computational geometry problem in which you have to place a certain number, the minimum cardinality number of guards that can observe the entire continuous boundary of a polygon. And a variety of successful heuristics have been developed to cover those spaces quickly. Other optimization methods have been used for discrete view planning, as well as random sampling, which is a method that we're going to advocate as well. And then there are some that have been developed specifically for 3D path planning. As I mentioned, there is the method of iteratively slicing over a structure and creating a loop that covers the entire boundary. We've seen that applied in a few different contexts, inspection of a building by aerial vehicles in this case. When you have an infinite field of view, you can apply a Voronoi diagram and that will obtain full coverage, although we're working with a definitively finite field of view, so we can't use this algorithm. It's also somewhat limited by the computational complexity that scales in the geometry of the problem. And other methods have gone about by partitioning structures into segments and developing sweep patterns that cover each segment. In the discrete realm of coming up with individual views that stop and take a snapshot of the structure, a common approach is to assume that some sort of what I like to call turntable coverage of objects, where the object is small enough that you can place it in the center of a room and look at it from a variety of vantage points. These are a smaller degree of freedom problems generally, in which you can actually map out the entire topology that maps from every possible view on this tessellated sphere to every primitive on in the model of the structure. But we're going to advocate sampling-based planning for the construction of a truly global 3D coverage path. And here's why. We believe that the ship hull inspection problem represents a coverage problem with low clearances. It may be the case that a single slicing direction that cuts across this with 2D slices may not necessarily find you a feasible path if a feasible path exists. And similarly, if you choose one orientation for sweep-based primitives, you may fail to find a feasible path. It's also scalable to high dimensions, and in the case of such an expansive structure, you may not want to map out the full coverage topology from every view on a discrete grid to every primitive in the structure. And so we seek guarantee of completeness, and that's one of the reasons why we're using sampling-based algorithms. And in fact, there are sampling-based algorithms for this task, but none of them have been shown to be complete. So this is a property we're very interested in, to be able to show in the limit, maybe hopefully in a short amount of time as you're drawing samples, you can guarantee that you'll find full coverage if a feasible solution exists. So typically this problem is broken down into two components, which really is a simplification of sorts. It's saying that I would like to have a minimum cardinality set of discrete views that observes the entire boundary of these structures. And then after you find the minimum cardinality set, you proceed with multi-goal planning, linking them together into a feasible inspection group. Of course, there is a single objective that could be used to represent this function, in which you have weights assigned to the cost of collecting a view and the cost of travel. But really, there are only a few catastrophic counterexamples where breaking it up into two pieces goes awry. And they tend to be in situations where you have an infinite field of view and you can move infinitely far from the structure. And this is certainly a case where we're in a very confined environment and we have a very narrow field of view. And I also want to note that we're sampling the structure boundary here. We're implementing a variation on the dual sampling method of Gonzalez, Banos, and Latone, where we actually sample components from the structure boundary itself, and then we map to a region of configuration space in which robot configurations are sampled that we know will map to views of the point on the structure boundary. Now, in our case, we have a variety of collision and occlusion hazards that can interfere with that, but we still pick regions where, at least geometrically speaking, we know that the sensor field of view contains the primitive that we're hoping to observe. So you see the samples tend to be relatively close to the structure, and we don't waste any time sampling out here. So here's an illustration of this two-step approach that I've been talking about. We sample configurations to obtain 100% coverage of the mesh. In our case, we have an algorithm, the redundant roadmap algorithm, that demands K coverage of some redundancy K. Maybe each primitive has to be observed 3 times. We then choose a set, plan a path that connects all of the views, and then try to smooth that path. So we'll bring together 2 different algorithm analysis concepts here. One from planning feasible paths, in which we care about random samples landing in worst-case regions that you need to join 2 robot configurations together. And another group of analysis problems in which there has been an interest in guaranteeing continuous coverage of the workspace in a number of samples that has appealing convergence as the number of samples goes to infinity. But what we're doing is adopting these tools to guarantee coverage of a discrete set of primitives rather than the continuous surface of a structure. And there are some reasons for doing that. We look at robot configuration space and workspace as a set system in which the discrete robot primitives are observed by configurations. And each configuration represents a set of primitives, and in turn, each primitive represents a set of configurations that maps to a view of that primitive. This framework has been used in analysis completeness that is appropriate to the coverage problem. And we also establish a theorem of probabilistic completeness that gives us exponential convergence as the number of samples goes to infinity. I had an interest in possibly working through the details of this proof, but I think in the interest of time I'm going to have to just give you the best parts, the summary of it, which essentially says in the limit, as the number of samples goes toward infinity, the probability of algorithm failure varies as a decaying exponential in the number of samples times the worst case volume fraction of any one of these visibility sets that maps to the sighting of a primitive. So whichever one of these happens to be the smallest and has the smallest set of feasible configurations, that's what determines the convergence of the sampling procedure. We're able to establish this invoking some tools from the analysis of probabilistic roadmaps and RRTs, and we adapted for K coverage. Unfortunately, I'm going to have to gloss over that and refer you to the paper, but it does have a few positive results. One of the things it shows us is that we really don't want to simplify the problem or reduce its dimensionality by taking 2.5D slices of the problem, because there could be cases where that actually takes our volume fraction epsilon and makes it far worse, when in fact a better epsilon exists by treating the problem as a full 3D problem. Even by plugging in some rather tough numbers into this formula, we're able to see that in cases of 1 million primitives, a very unappealing volume fraction, and K equals 10 coverage, the probability of failure still hits 0 in a pretty reasonable number of samples, between 10,000 and 100,000, which we achieve in a minute or two in the actual implementation of this algorithm. So the outcome of this analysis was that the view planning routines we hope to show were probabilistically complete. They are probabilistically complete, as are the multi-go planning routines. They're governed by decaying exponential functions. There's just one case in which the two components put together might give you a problem, and that's a case in which you have a robot entrapped in what I call as a prison cell. If the robot's actually allowed to be sampled in a location where it can't get out and move to other areas of the configuration space, then that becomes problematic. So, we have a feasible route that obtains 100% coverage of this structure. We've shown that the algorithms that exist for doing this are probabilistically complete and they have appealing convergence. But we believe that there's room for improvement here. And in particular, we define this local problem of wanting to move a configuration Qj to a location of minimum distance relative to its two neighbors, j minus 1 and j plus 1. We hope that by doing this iteratively over the course of the inspection, we can make improvements and both shorten and improve configurations out of the tour. And we have a heuristic that does this pretty well for our case, in which we have a large, densely packed set of views. But when the views are not as close to one another, and the components of the structure might be disparate and far apart from one another, we can also use the RRT star algorithm and insert it to obtain a path that gets us to this region of constraints where configuration Qj has certain coverage constraints that it and only it sees over the entire structure. We need to make sure that all of those constraints remain satisfied. And so this RRT star algorithm can in fact be used as a subroutine here to get us feasible and increasingly better paths to this constraint region from Qj1 and from Qj plus 1. And we can link these two together into the inspection group that I showed you earlier. So here's some computational results. In the interest of time, I'll have to go through these a little quickly. As the number of configuration sample increases, the improvement procedure makes great improvements to the lengths of the tours and the number of configurations in the tours over two different ship models that we obtained from real data. Especially over the first 10,000 samples, it's very productive. In 1 to 2 minutes, you have pretty significant improvements in both the length of the tour on these two ships and the number of configurations of the tour. Here are some visual examples of the type of local improvements that can be made using the improvement procedure over this 2-hour simulation. Local portions of the tour are brought into near perfect alignment using this heuristic that tries to bring one configuration into good alignment with its two neighbors. Similarly, we obtain good results in this ship model. And just a quick snapshot of some field deployments, since I'm running out of time, I'll just show you a glimpse of this. We got the chance to actually go back to one of the ships we used to build one of these mesh models, and we implemented a plan path that was smooth using the smoothing algorithm. We were able to determine that certain areas of the structure were slightly distorted in the model, and we obtained information about, more accurate information of their structure by going in at close range. We saw how narrow the propeller in fact is as opposed to its geometry in the model, and we certainly obtained some improved information about the structure of the rudder and some of the propeller struts. And we were able to actually smooth and improve our mesh model through revisiting the ship using this higher resolution plan path. So, okay. And in conclusion, so what we propose in this paper is a comprehensive methodology for sampling-based design and analysis of geometric inspection routes, a probabilistic completeness analysis that applies a robot coverage path plan, uniting concepts in path planning and sensor placement methods. And in addition, an improvement algorithm that iteratively shortens and smooths feasible paths, and some snapshots of its field implementation. So I'll point to a few colleagues at ONR, MIT, UMich, Bluefin, and Seabite who helped out with this work, especially with the field deployments. They were very helpful, and I'd be happy to take your questions.
That will be very basic questions, so I apologize.
Sure.
The sampling, you do it often, right?
Yeah. We do it offline.
So what is this random variable that you sample and then apply the channel?
Sorry.
There should be some random variable that you sample IIIa, and then apply the analysis using Curving channel.
Yes.
So what is this random variable?
Well, in the area that I went into a little depth, I was talking about the view planning problem, where you're sampling a robot configuration and you're looking at what set of discrete geometric primitives it collects using its sensor. And in the analysis in particular, you're looking at whether that sample is going to hit the region of worst case volume that maps to the feasible views. And so the analysis is bound using the worst case volume fraction.
How is related to channel? How you use channel? What channel requirements do you do that?
It's a binomial distribution, and assuming the limit of samples is large, we treat it as Poisson, then we bound its behavior using the turn-off bound, and then from that we can obtain an exponential function that governs its behavior in the limit. But in fact, let me go back to that slide.
Channel
I regret that
channel bound comes to a bound distance to the mean. What is the meaning of mean here?
Well, what we have here, again, the Poisson distribution parameter is the expected number of successful hits in our sampling process. So it's comprised of the number of samples times the worst case volume fraction.
That was my question.
Okay.
I had a much simpler question. If I understand your technique, you sample and choose these viewpoints, and then you connect them with a tour, which you then improve.
Yes.
Do you select the viewpoints without regard about how easily they are reached?
Yes, we treat the view planning process as an independent problem.
So could you end up with a viewpoint that you really like because you can see a lot, but in fact it's really hard to get there?
Yeah, and in fact, in the paper there are some details about the improvement, the iterative procedure that we use to get the final set of views. But we do end up taking into account the distances between the views. We do it using a lazy algorithm that was developed by Saha and Lateau, where they initially assume naively that Euclidean distances govern point-to-point distances. And then you solve the TSP, update the distances, and iteratively update using sampling-based point-to-point path queries until eventually you have a pretty good, it's kind of stabilized at a local minimum, and you have a pretty good idea of the actual point-to-point distances without having to go from every point to every other point and do n-squared path queries.
So that's a local improvement thing. Or do you have theorems as well for how well that'll do?
Yeah, we're able to show that that routine is also probabilistically complete and governed by exponential functions. The only caveat is when you put the two together, you can have these strange and obscure counterexamples where sometimes it might not. Which I mentioned one of these other slides. that slide right there.
Okay, thanks. Oh my goodness. Thank you very much, Brendan.
Okay, so this brings us to our third and final talk in this session. It's on trajectory optimization for real-time replanning in dynamic environments. And the work is by Chongyong Park, Jia Han, and Dinesh Manocha, who will be giving the talk.
Thank you very much. I guess I'm the last talk, standing between you and the front, so I'll try not to exceed my time limit. I'm Professor UNC Chapel. They're two of my students. They're both interning at pretty good robotics companies, therefore could not come. So I'm the bad spokesman here. I'll talk about motion planning. I think the previous couple of speakers did a good motivation of that. I won't spend too much time. This is a classic problem in robotics that you find collision-free paths called collision configuration, final configuration. Pretty well studied for the last 30-40 years, and now I'm going to spend time on that. Besides robots, a lot of other applications like gaming, we saw on top of swing, and the last talk about garbage planning, they all deal with this kind of problem. Basically speaking, this is a very high-dimensional topological search problem. That's a challenge of this problem, and high-dimensional is where the challenge comes from. Now, for today's talk, I'm going to focus on dynamic scenes, that you're moving obstacles. Unlike the previous talk, you just saw about that. And you don't know how obstacles move. And this is how we all humans deal in real life. So the challenge comes up as the following, that they big talk about increasingly human-like environment. That human and robot should work together as co-workers. And as a human is taking action, the robot should react to it, and vice versa. So the robot doesn't know much about how humans are going to work out, and it's a high-dimensional problem, you deal with it. One of the biggest challenge comes out to be the case that you can't make assumption about the motion of the obstacles. So human is a good example of that. There are lots and lots of work where people have done assumption on the trajectory of the dynamic obstacles, that obstacles are going to move in a certain path or certain trajectory. That will not give you freedom to choose. But now, unfortunately, you don't have that thing. You're already dealing with sensors and sensing real time and upgrading the planning scheme in real time as well. Of course, since you're dealing with the sensing, you need a real-time planning because the environment around is changing drastically. So any plan that you have to do, a key component is real-time and speed, because a lot of planning work is offline. In this environment, you're just going to do offline planning because by the time you do the planning, the environment has changed. So the planning has to really go and adapt to the environment, go around with that. And especially for our robots, we also decided to do smooth paths. And I'll explain more about the smoothness component. It's both for the physics of the robot as well as the reason smoothness comes in. So the classic concept, it goes back to Tomás Lozano-Pérez's work in 1970s, notion of using configuration space from topology. That given a robot with the degrees of freedom, you can have a notion of configuration space, and you can decompose the configuration space into collision-free space or C obstacle space. So the collision-free space and obstacle space. So obstacle space is an example of like a simple robot that can manipulate with 3 degrees of freedom. And if you look at the different angles like theta 1, theta 2, theta 3, you get pretty complex functions. In fact, the complexity of computing exact configuration space is exponential. It's been known to be piece-based complete problem. Even people trying to compute configuration spaces can struggle beyond degree 3 or 4. So in some way, the reasoning in configuration space without having the explicit representation of configuration space, and that's where planning becomes pretty hard. So the path planning problem reduces to the fact that you compute a collision-free path from initial to the final space. So this kind of blue region is the obstacle space. You want to avoid the path. This is two configurations shown right here and here. You compute a path, and you don't want to go to this region. But this is a classic example. In our case, we're dealing with dynamic scenes. So what does dynamic scenes do to you? That this configuration space that we see in most motion planning textbooks is no longer constant. It's changing. So just imagine, it's like traffic. When you're driving, when humans are moving in a crowd, the environment around you is changing. So you just cannot assume some big pre-computational configuration space, some explicit or implicit, and deal with it and how you deal with it. Now, there's been a lot of work in motion planning, which I'm now going to survey for lack of time. But I would say at a very broad level, this is our very broad classification. The two kinds of methods, one is our random sampling, just on the previous talk, in the context of coverage planning around the shift hull, and the classic notion of optimization, some kind of a continuous formulation of this. So here's a very quick overview how they work around this case. You don't have any explicit representation of configuration space. This is how they work. So you don't have explicit representation. In random sampling, you basically generate all the samples based on random distribution. You figure out the collision checking which are in free space, and the one which is in free space, you tend to join the nearby ones and do some kind of a graph search and figure out the first off the stop. We do a very simple A star search, but you could do some more better on the A star search. So this is all assuming sampling, but again, this really works well in environmental sampling. But the second problem with this is that generally you do not get smooth paths. For example, a lot of robots are dynamic constrained. It is hard to get dynamic constraints like a post-process select that repeat this log smoothness. The second approach is goes back to the potential field method that you estimate some kind of a path on the right hand side based on some initial guess. You can see like a straight line. And then that collision happens, you can refine the path, some kind of optimization function. And you hope you keep on the optimization process that the whole path is collision free. But at least this approach can give you smooth paths. These are two classic methods that are pretty well studied. Now, why we can't directly use any one of them? So I will not survey a randomized method, the two classic being PRM or RRT. They really, work pretty well for static scenes, but they're limited to very similar dynamic constraints. So if the motion and if the mode is static or moving very slowly, you can do it. But the kind of application we are looking for is very high dimensional robot with high dimensional environment scenes with a very fast changing environment. It will be very hard to make PRM methods work in that kind of environment. So the optimization method actually goes back to some of the earlier work. You can date back to the 80s from potential field method, the classic paper achieved in 1986. There were a lot of variants of that, how do you optimization. And they can at least handle dynamic obstacles because you recouple the potential at every time frame instantaneously. And if the obstacles move, you can really update your environment potential field and do the new path computation. Most of previous work are low dimension. But they also generate smooth trajectories. This is the natural formation of that. But the biggest challenge they have, which I'll come back to, is they struggle with local minima. That you're doing a local optimization strategy, and if your initial guess is not good, or if the obstacles are moving too drastically, you can totally get stuck. So part of the problem we're dealing with here is that how can we overcome this problem? More recently, there were two recent optimization-based methods, which is actually we have work is based on. They tried different kind of what's gradient optimization or stochastic optimization. This one's called CHOM, and this second one is called STOP. So the idea here is that you discretize the vector to waypoints, as you saw in the animation. Come with some cost function, I'll talk about that. And you use a gradient to move the waypoints to the minimum total cost. So this is how you formulate the optimization function in this case, and you repeat the problem. And the STOP work, which is done at USC and Belo Garage, they use some kind of stochastic gradient, and also the good thing is you can take into account torque and orientation constraints. So these methods have been used and they're also deployed on physical robots, show good well, but I'll talk about limitations soon. Besides these two methods, there's been a whole series of work on dynamics environments. And again, due to the lack of time, I won't cover it. This is a very small sample I'm showing it. The classic work on velocity obstacles, which are designed for motion planning and dynamic scenes. Typically limited low degree of freedom robots, some nice work on inevitable collision states, as well as real-time planning. In fact, we use some ideas from Chris House's work on real-time replanning, which I'll talk about it. So let's go back and see some of the data optimization methods, how they work. So you can see this is how they pose the optimization point. They describe the trajectory to these waypoints, and they come up with some kind of cost function. There are two parts of the cost function. The first term, so-called C, is kind of a collision cost. You want to avoid collision. So you want to move the waypoint in a manner it avoids a collision, and the way they do it is they pre-configure what is called a distance field. So if you're given a static environment, at any point in the space, you can figure out for this point what's the total strain obstacle, and you keep that as the distance field. If it's a static environment, you can pre-configure the distance field, and based on the distance field, you come with the optimization function, it takes a collision cost. And this is a second matrix which takes into account a smoothness trajectory. So if you have a maximum force constraint, torque constraint, you can pose that. You can clearly see, so the objective function is a combination of computer smooth trajectory which avoids collision. That's what you're trying to do. And you combine that to trade on this based on initial estimate. Now what happens, this actually works okay for static scenes, but what happens in dynamic scenes? So first of all, distance field computation which is done is actually, the pre-computation is quite slow, the lookup is fast. If you give a dynamic obstacle, even small motion, the distance field is no longer valid. Or there's at least non-local region, the distance field changes. So you can't really use this for distance field directly because you are updated. And the second idea here is now that these people do wrong planning before execution. The idea here was, you given a static scene, you can take a little bit of time, perform the computation of planning, and then execute the whole planning on the real robot. But in a dynamic scene, you can't afford that because by the time your planning is done, the environment has changed. So this framework doesn't really deal with that anymore. So to overcome the problem, this is just a thing that they can do this kind of problem. But the assumed static environment, performance is slow, and I keep on saying this apart, I don't mention to you, you're very susceptible to the initial seed value that you use for this kind of optimization method. The seed value is good, like they use a simple collision-free path, you can do it. Some of the recent work people have done, they actually take a sample-based planner, computer collision-free path, use that as initial guess, and refine the path based on optimization. But again, this is assuming you can compute a good path by this thing. So how do we overcome some of these problems and deal with it? So we're dealing with a dynamic scene where we can't make any assumptions about the trajectory of the obstacle. So it's really impossible to do long-term planning because the environment has changed and environment is going to change. So we take what kind of notion of interleaved planning with execution. We plan, execute, plan, execute. It's a real-time loop running continuously. The good thing is you can handle dynamic environments, and what we present is a scheme which not only takes into account collision avoidance of static scenes, but we also bring how you can avoid collision dynamic obstacles. Again, doing everything real time. And the smooth path computation is similar to the work that's done in Chomp and Stomp. We follow that quite directly. But the main challenge here is to improve safety. That as the environment is moving, we do this very quickly. So we come with a whole different optimization formulation to do that. But again, how do we achieve the real-time performance? That's a very hard quantity to get. So one second thing we bring on this is that this is all about search. Search in high-dimensional configuration spaces. Why don't we do this search in parallel? Improve the probability of search by parallelism. So we bring parallelism in two ways, and this is not very expensive parallelism, it's a commodity parallelism, that for each iteration of the optimization process, you parallelize the computation, so you do it much faster, which is very important because you use real-time planning. You're interleaving planning with execution, so you want to do this planning much quickly, and to at least reduce the damage that happens because of initial seed, we take multiple paths in parallel. And if we have the path with some guarantees, you think we're basically getting a larger coverage of seed space. So the chances of getting stuck in local minimum decrease. We cannot eliminate that, but it's much better than doing sequentially. So the overall benefit we get is more because of parallelization. We get much better performance, things move quickly, but because we're doing a parallel search in multiple paths, we get the company of much better path which avoids collision with the obstacles. So let me come back to the more details about this. And as I said, we don't have any explicit representation of the motion of the obstacles. So what we do right now is take some recent estimates of position and do some extrapolation. And again, we can only do local extrapolation. So the obstacle might change. So we are exactly there doing some very conservative approximation to the extrapolation and say that if your neighbor, based on the past history, obstacles are moving, hopefully there will not be a big change. And the whole framework now works like this, that you basically step up based on your computation, first planning in step 0, based on the planning in step 0, perform execution in step 1. You can at the same time planning for the step 1 in execution. So this whole planning and execution is working in parallel. And depending on how much parallelism you can have, how much computation you can do, you can make these time intervals really, really small, and I'll show you that we can do. And the idea is, so yes, it's dynamic environment move, you upstate the sensor data and do this. So this is the whole just framework of the motion planner, how we deal with it. So you're given some sensor data, which is where you're getting latest position of the dynamic obstacles right here. and the planner moves in the view box and gives the execution plan to the remote controller at the bottom. This is how the real-time module feedback loop is working.
Now, how do we actually modify the actual obstacle thing?
So the basic idea of optimization is that we still assume the world consists of static and dynamic obstacles. So for static obstacles, we use a pre-computed distance field, which is only valid for static obstacles. But then we have a dynamic obstacle, a totally different than. And the idea is that we can use another term that break up the collision cost into CS and CD, CD for dynamic. And we deal with the dynamic obstacles.
We perform some bounds on the motion.
And based on the bounds, we have some motion bounds to local trajectories. Remember, trajectories only have to be good for the duration of the planning interval. And as we do more and more planning in parallel, this interval can be made really, really short. And we compute this bound on the local trajectories, perform some bounding volumes, and this whole collision checking based on computing bounds is happening instantaneously. And I'll show you a bunch of examples to show this stuff is actually quite quickly. The key here is again, how do we compute this bound? So this is probably one of those figures, which I think at the end of the day is going to be a little hard to understand. The notion is an example of a configuration space in 2D. This is a configuration space, and I'll ask you to sketch your imagination. Along the axis T is a time changing phenomenon. So the idea here is to show the configuration space actually changing. Now when you're given a static obstacle like this, life is good because your configuration obstacle space is changing. But when you're dealing with dynamic obstacles of this type right here at the top, we're computing conservative bounds. So this is where somehow the configuration space is changing, and how do you work out the bounds on this? So I'll ask you to read the paper. I don't want you to really bog down the mathematical details. And how do you compute conservative bounds for obstacles, which can give you some local directives for collision checking. And this is what you take into account in your optimization formulation. As I said, the second part here dealing is with parallelization. Parallelization is very critical here to guarantee real-time performance. So as I said, the previous method was pretty slow and quality was bad. So we really want real-time performance and parallelization. So this is not some very fancy parallelization. We do two kinds of parallelization. One is that you exploit multiple threads. This is which is supported by all commodity multi-core and many-core algorithms like this. So you take multiple threads and you really take different initial seed values. So it's really expanding your search space by taking multiple seed values and do that. And we do two kind of parallelization, both on commodity, one is commodity multi-core as well as commodity many-core, which is GPUs, it's graphic processing unit. This is nothing fancy. In fact, all the laptops that you guys carry have this parallelization. This is just an example of a data center processor. We use a 4-core processor. Most of the CPUs are to 4 cores like that. But there's a lot of work we have done, and something which I'm not finding much at this conference, that a lot of it's about search, and people are not parallelizing search. We talk about doing search very quickly in 3 milliseconds, but we're not exploiting the parallelism that's available in all commodity processors. This is an example of GPU controllers. We think GPU stands for graphic processing unit. Now just to give you an example of the two serial line GPUs by two big companies, AMD, IIIa, and NVIDIA, the theoretical marketing numbers are teraflops. So we go with that, but this is it. But we parallelize on both of them, and as I said, we reduce the iteration time for single optimization as well as perform multiple optimization in parallel. The more parallelism you do, the quality of trajectory improves, and we can show bounds for that. So just to show some numbers, this is an example of, on CPUs, how much iteration per second you can do. As you can input the number of cores from 1 to 4, you're getting close to linear scale up. Now GPUs are very much lightweight cores, but there are lots of cores much lighter weight, and in this case, we were even doing up to 10 trajectories, and if there are more trajectories, more stuff to be done, GPU can be exploited more. So if there's more computational power, GPUs can be really good commodity processors for that. So this is an example of a success rate like that, and I'll show some more example of that. So if we also do, how does parallelization manage? So these are some parameters we use based on normal distributions of initial seed values. If we give a pretty open environment to pretty narrow environment to type fittingness, and how much is the solver sensitive to the initial values. I'll refer to the paper like this to show that in the more challenging environments like this, you get about this figure or this. So here the goal is to show that as the more and more challenging environment, the parallelism actually helps you more. So this is all running on your laptop. There's nothing fancy going out here. Just show you the example of this. Right now we got a simulator. We took the work with Willow Garage. They were geared to robot with 270 arm. For our sensing simulation, we did 30 millimeter of accuracy. That's what Willow Garage allows you. And the basic aerodynamic obstacles is we're sampling them at about 200 milliseconds per frame to get new position and velocity like this. So here are a bunch of some graphs. You can read them in the paper. People want to know that what happens if our sensing error becomes very big. Of course, since our computation bound is kind of conservative, we can take it, but of course, if it becomes much bigger than 250 millimeter seconds, then we may not compute that part. Because your sensing error is big, you like to get very conservative bounds, and when you do a search, given a limited time frame, there are times the path may not converge. You may not compute a collision-free path, but for up to 100 millimeter sensing error, you're seeing pretty good thing. What happens if you do this kind of very obstacle space? So we did a lot of simulation by looking at high speed versus low speed obstacles, and you can see how the difference matters. Let me just line up and number obstacle. Let me just show one video and we'll wrap up there to show how this comes up. So this is a raw simulator, and we want it to be human-like scenario here. So the human is moving, robot or nothing about this disappear to simulator. So human comes close to robot, according to the rendering, and the robot is basically the whole real-time planning to avoid obstacles with the human in this case. So this is kind of a scenario we are looking at where the robots and the human come together. As the humans move, the robot knows nothing about it, but the robot adapts to the human. So this is the way we want to work with Willow Garage. We're going to implement into the hardware and ICAPS in a raw simulator and this thing. This is just an example of parallelization. You will see multiple trajectories in green color. So basically searching all of them, and we take the one with the minimum cost. Just showing the benefit of parallel search and how to do the trajectory computation. I think I should wrap up before my session chair gets too mad at me. Just to conclude here, this is example of this thing, but there's still a lot of work to be done. There's lots of sorts of uncertainty we don't take into account. And as I said, we compute bounds, which tend to be conservative to this thing. And of course, we are improving the search, but it's still giving local minimum guarantees. Our goal was not harder. Just to conclude, what I presented to you, the optimization motion planning algorithm, is very general approach to compute smooth paths. I keep on emphasizing it's generality. You don't make any assumption on the robot or obstacles itself. And we're dealing with very high degree of robots in a robot like this. The core goal is to do real-time collision avoidance, achieve the performance by parallelization, which also gives us better path quality. So thank you very much. Questions?
I certainly have one.
Go ahead.
You spoke a bit about the formalization of your optimization objective and the components that were involved. Can you say a little bit more about the actual solving procedure that lies underneath your planner? How do you solve that optimization problem?
Yeah, so the solve, so in this case, we actually, the ultimate solver we build on, like for stomp views, is stochastic optimization. In this particular case, we use stochastic optimization. We formulated the formulation there, and we use the original solver, the stomp views, stochastic optimization. That's a pretty standard method.
What solver, do you know what the actually solving algorithm is?
It's a pretty consistent optimization problem. I look at the MATLAB-based solver.
MATLAB.
I think the MATLAB-based solver. But that itself, I don't think in this case, what solver we use was not the most critical point. It was basically decomposing into how do you deal with static obstacles, and how do you deal with the smoothness constraints, and how do you deal with dynamic obstacles. So that decompositional problem was more critical here. We did not really at least evaluate how much different solvers we could make with every difference. I think we are more sensitive to this choice of the initial seed value than to the particular solver.
Okay. Would a global solver eliminate this problem of local?
If you can give me one, of course. The question is, can you do them in real time, of course.
Yeah.
I just start the assumption that you're dealing with a very high dimension configuration space where real-time global solving is almost next to impossible. That's my assumption. So if you can change that, I'll be very happy.
Other questions?
I have a question. Just out of curiosity, your videos were when the human was nicely moving but not being adversarial in any etc.
Sure.
So when you start to push the limits and suppose the human wants to be a little adversarial, where does it work, where does it not work?
Yeah, so that's a very good question that, if you can always come with this, outsmart my scheme. And, for example, in this case, we just played with the example adversarial. We took simple object classes like just simple spheres. Or what if you move them really fast? Even faster than what your sampling can keep up with. So, of course, in that case, your planner would fail, it won't find a path. This example adversarial. And in this case, as I said, we should example a success rate. And if you really start moving very fast, you can really outsmart. So anything you do, we are really planning this much time frame, and if your speed is much faster than that, then of course it won't.
Then whenever I think of these things, I believe that there is a notion of reaching the goal, and then there is a notion of avoiding collision, which can be very reactive.
Right.
So if there is an obstacle which is moving very fast, maybe I should forget about achieving the goal and just be reactive and try to avoid the obstacle for now.
So that's a very good question, but I don't even know. See, I'm dealing with a totally unknown environment. I'm only given some recent samples where I can probably extrapolate the history. So if I knew that there is some very nasty obstacle, adversarial obstacle there, then I can perhaps take an optimization procedure to suggest doing what you're doing. But they're already assuming you know something about the environment. So this is all about, if I knew something about the environment, I can make much smarter decisions. But in this case, our goal was to go with purely general frame. And if you can somehow infer this information environment, yes, you can change the optimization procedure and take the constraint that you will suggest.
Thank you very much. That concludes the session. I think there's something in another room right now.
I'll give you my slides, or you
That
can
would
get
be wonderful. Thank you.
Thank you, sorry for the
No, it's always fun to have a movie.